Welcome back. This is the first lecture of the two lectures on cyclic voltammetry. Cyclic voltammetry is perhaps the most common electrochemical technique. Every lab, experimental lab does it. Every theorist should know how to interpret, at least qualitatively, these experimental results. So if you want to add electrochemistry to your resume, you should know the CB. It is quite a complex phenomena. We may not be able to do justice to all quantitative aspects with these two lectures, but our objective is to at least give you a brief overview of this technique and how to interpret the experimental result. As I said, the scope of the set of lectures on experimental electrochemistry is quite narrow because of the time constraint in this course. But maybe at a later stage, I will add many more lectures on cyclic voltammetry, how to model it quantitatively, more quantitatively. So what do we do here? So we have a working electrode. Onto the working electrode, we impose a potential. And the potential scan is of the following manner. So we increase the potential of the working electrode, first, let's say in the anodic direction, and get to a maximum potential, and then we switch the direction. Then we decrease the potential. This is called a cathodic scan. And then we do this repeatedly. Okay, so anodic scan is followed by cathodic scan and so on. So we are plotting the potential versus time in this plot. So typically, when you do this experiment, the first two cycles or first few cycles are not taken into account because you are probably cleaning the surface, reorganizing the surface. But beyond, let's say, the third scan, the results are taken quite seriously. So a mathematical way to describe the scan is the following. This is called the scan rate. Okay, so the way we impose the potential looks reasonably simple. But let's understand the implication of the potential scan gradually. So first, let us analyze the experiment without taking into mass transfer effects. So we consider our typical electrochemical reaction where an oxidized species reacts with the electron and gets reduced. So we can define the OO potential once we know the potential of the working electrode. So once we know the concentration of the relevant redox couple once we know the concentration of R and O in the electrolyte, we can define the equilibrium potential. Once you know that, you can also define the OO potential because the potential scan is known to you. So based on this and based on what we know, we can use the Butler-Warmer equation to anticipate what would be the current. So this information is fed into this, and for the system under consideration, for example, this system, we know alpha A and alpha C. If you don't know, you can assume it to be 0.5. And then you know the exchange current density with you. Let's say you start the system with a particular concentration of O and R. With that, you can also anticipate what is the exchange current density. We have addressed this in some lectures in the past. So with this, we can get what is the current. In addition to this Faraday current, there is also capacitive current. Why? because capacitive current is given by capacitance, which is assumed to be independent of potential in this case. And then we have dV by dt, because that's a time varying potential scan. So from this, we know the capacitive current. Putting these two together, we get the overall current of the system, and it would appear something like this. So this is just a straightforward map of these two equations. So as we move along the anodic direction, after a certain point, the Faraday current kicks in and it raises exponentially, because O potential for the anodic reaction keeps increasing, it raises exponentially. And same along a similar logic, when you go in the cathodic direction, beyond a particular minimal O potential, the cathodic current also raises exponentially. And because the scan rate is uniform, the capacitive current is also uniform, just that it changes sign when we go from anodic scan to cathodic scan. So this dark line indicates the plot of this equation. This is the capacitive current. When you add the capacitive current to the Faraday current, you get the dotted line. Okay, so this looks simple enough. So what are the issues? The issue to be noted is that we actually have not taken mass transfer effects. What do we mean by that? Even though we know the concentration of O and R when we start the reaction, the concentration of O and R keeps changing as the scan is being imposed on the working electrode. Voltage scan is being imposed on the working electrode. So what is happening here? The species O is being transported from the bulk or near surface region to the surface of the electrode. And when this reaction occurs, there is a decrease in the concentration of O near the electrode surface. Because of this decrease, a concentration gradient is established. Because of the establishment of this concentration gradient, there is a transport of O to the electrode surface. Likewise, because R is generated at the electrode surface, at the electrode-electrolyte interface, the concentration of R is highest at the electrode-electrolyte interface. And because of this concentration gradient, there is the transport of R from the electrode-electrolyte interface to the bulk of the system. So even though we know the concentration of O and R at the beginning of the voltage scan, we really do not know what is the concentration of O and R just near the electrode surface once you've started the scan. So what are the unknowns? Again, we know this, we may assume alpha A and alpha C, but exchange current density is an unknown here. Why? Because we know the formula for exchange current density. So if you assume alpha A and alpha C to be a particular number, you can write the expression for exchange current density. We have done this in some previous lectures, so please go and refer to those lectures, how you get this expression. So exchange current density crucially depends on CR and CO just near the electrode-electrolyte interface, and that is an unknown. Okay, so you really do not know the concentration at a given instant of time during the voltage scan. Okay, so exchange current density is an unknown. We can make an approximation for these issues if we can assume a completely reversible system. Okay, so what do we mean by that? If the activation energy for electron transfer for both cathodic and the anodic reaction is very less. Okay, so note, we are only looking at one electrode electrolyte interface. So O can get reduced and R can get oxidized to O. Okay, so there are two possible reactions, oxidation and reduction occurring at the single electrode electrolyte interface. If the activation barrier for both these reactions is assumed to be negligible, the system will always be, I mean, such a system wherein the activation barrier is very less is called a reversible system. So we can use the Nernst equation in that particular case of when the kinetics is very facile and the system is considered to be reversible. So using just the potential of the working electrode, it is enough. This potential is enough to establish the concentration of O and R near the electrode surface. So from this, we can make some qualitative assessment on what is going to be the effect of mass transfer. So we plotted this in the absence of mass transfer. So under the assumption of reversible kinetics, we can use the Nernst equation to qualitatively sketch what would be the modification of this plot to make it more realistic. So what is our expectation here? So as we cross the equilibrium potential, okay, so the driving force for oxidation increases as we go to more and more anodic potential. Okay, so this peak is because of increased thermodynamic driving force, which will increase the oxidation reaction as we go to more and more anodic O potential. But as we keep doing that, it is also, there is another effect which we need to consider. As we go in the anodic direction, the concentration of O keeps decreasing. So even though there is a greater thermodynamic driving force for oxidation, because of the decrease in the species that is to be oxidized, in this case, the species that is to be oxidized is R, that keeps decreasing. The concentration of R keeps decreasing. A convolution of both these effects, that is the concentration of the species that is to be oxidized and the thermodynamic driving force for oxidation, both these things convolute to give rise to a peak, and beyond a certain point, the current keeps decreasing. So we are plotting the anodic current, and this is the anodic O potential. And in this here, there is the cathodic O potential. Likewise, as we go change the direction and scan becomes cathodic, we can also argue in a similar manner. Beyond a particular point, the thermodynamic driving force for reduction reaction, that is O getting reduced to R, that gets it keeps increasing, and a convolution of two aspects. This aspect of increase in thermodynamic driving force and the concentration of the species that is to be reduced gives rise to a cathodic peak. So this is a qualitative interpretation of what might be happening in a realistic system. Why is this interpretation even valid? Is because in reversible electrochemical system, the qualitative, this qualitative feature of cyclic voltammetry that we just argued based on physical arguments is actually seen in experiments. So there is certain validity to this kind of interpretation. So what we would do in the next lecture is to provide a slightly more quantitative treatment. At least we will mention the relevant equations that need to be solved more thoroughly to get the quantitative treatment of cyclic voltammetry. So in these two brief lectures, there's no way we can do justice to quantitative treatment of cyclic voltammetry, but at least I want you to get a qualitative feel for interpreting cyclic voltammetry. Thank you.